Hello, this is Stacia Gordon. I'm just here to give you an overview of the field area that I'll be discussing tomorrow in the field example where we use StraboSpot to take a variety of measurements, document samples, as well as the overall petrology and rock types at different outcrops. And so this is all based on fieldwork in the Ruby Mountains-East Humboldt Range, which is a metamorphic core complex in eastern Nevada. This is all fieldwork that was actually just done about a week ago. So just to orient yourself, here is a map on the left that shows two main things for Western North America. The regions where we have exposed arc batholith belts that are shown in this kind of orangish, pinkish color. And then in black is where there are this series of metamorphic core complexes that are found all the way from southeastern British Columbia, beginning with the Shuswap complex up in the north and continuing down to the south into northern Mexico, with the southernmost core complex being represented by the Sierra Mazatlan. And so each one of these core complexes is really a window into deep crustal processes that were active anywhere from the Cretaceous to the Miocene. So they're kind of in important areas to give us insight into the deeper processes, whereas a lot of the rocks around them are much more shallow. And so today I'll be discussing a little bit or give you a little background of the Ruby Mountains-East Humboldt Range metamorphic core complex that's found here in eastern Nevada. So just zooming in on that, here's a geologic map of the area. And just to orient yourself real quickly, if you look up at the legend here, you can see that the different colors represent different ages of rocks, and these are really the protolith stratigraphy of these rocks. And so overall, these high-grade metamorphic rocks that form the core complex are exposed in two main ranges: the Ruby Mountains down here on kind of the more southwestern portion of the map, and then in the East Humboldt Range in this more northeastern portion of the map. And the reason why, in this case, this map is shown by the age of the protolith is that there's a really well-defined stratigraphic section that forms the protolith to all the rocks found within this core complex. And so this slide is just showing kind of that general stratigraphy. And don't worry about all these different names. Just know that we have a range of sediments that range anywhere from the Neoproterozoic to the Permian. These are all passive margin sediments. And so the rocks that are found within the core complex and essentially in the footwall of the Ruby East Humboldt detachment fault are parts of this sedimentary package. And at the deepest levels, you see Neoproterozoic McCoy Creek group rocks, and then up to Devonian Mississippian graphitic schists. And so it's really nice that we have this stratigraphy and that we see it in other parts in Nevada, and that it's really well documented, in particular in terms of the stratigraphic thicknesses of these different formations, because then we have a chance to see what happens to those rocks once they're metamorphosed and deformed. And in particular, again, just looking at how the thicknesses of these units change. So overall, those rocks within the core complex, they have been studied by numerous groups, and what's been discovered is that they really record a pretty long-lived tectonic history. And so on the right here is just kind of a summary of some of the major events, where some of the politic rocks show evidence for early Cretaceous metamorphism. Those rocks have been extensively intruded by multiple melt generations. A lot of them are pegmatitic and granitic in composition, and they have melt crystallization ages anywhere from 92 to 29 Ma. There's also evidence that these rocks underwent an early decompression and partial melting event prior to the core complex development, and as early as the late Cretaceous in terms of that decompression. Whereas the core complex development in terms of the detachment fault being active and slip occurring on that fault did not begin until about 27 Ma based on mica and alkali feldspar potassium argon and argon argon cooling ages. And so now on the geologic map on the left side of the screen, you'll see that we've overlaid kind of these kind of patterned lines on top, and those are just showing you myelinite zones. And in general, the lines are representing the overall stretching lineation associated with those myelinites, and that's really showing the slip along that detachment fault and kind of the evolution of that core complex. And so just to give you a sense of what the outcrops look like within this area, hopefully in this cliff face, you can see that there's a lot of white looking rock, and that's some of that pegmatite and granitic intrusions that's pretty pervasive throughout the entire core complex. There's also some darker layers in here. Those tend to be those more schistose layers that are now just lenses within abundant melt or perhaps within quartzite or marble. That's pretty ubiquitous within the section as well. And those schists likely underwent, there's lots of evidence that they themselves underwent partial melting, but then were also intruded by abundant melt as well. So one of the reasons why we're interested in doing some work there and why we did the field work last week is even though there have been numerous studies that have looked at the petrology and geochronology of the Ruby Mountains-East Humboldt Range, it seems like there's still a lot of parts of the geology that could be understood because it seems pretty complicated. And just to give you an example of that, what's been documented in a couple of studies by Halle and Spear in 2014 and 2015 is that you see big differences in the overall tectonic history across very short spacing within the overall metamorphic core complex. And so in the upper left here is a cross section going from south to north, and this is within the East Humboldt Range, so the part of the core complex in the east. And just looking at two areas that have been well studied, this Winchell Lake Nap that exposes a large fold of some of the stratigraphy that I had shown you earlier, and then just south of that is the Lizzie's Basin block. And so in these two studies, they looked at the petrology as well as some geochronology. And on the bottom here are the pressure temperature paths that were interpreted from that petrology for those two areas. And you can see that they're quite different, even though really these two areas are only about 10 kilometers apart, if that. In addition, in the Winchell Lake Nap area, with this folding, there also seems to be pretty severe attenuation of the rocks, and this is where having that well-known stratigraphy is really advantageous, as we know how much those rocks have been attenuated as to how their thicknesses have changed, versus in the Lizzie Basin block, you don't see that same attenuation. And so we went in to do some field work in some of the areas that aren't as well studied to continue to contribute new information about that pressure, temperature, time path so that we can better understand how this core complex developed through time. And so in terms of kind of the cast of characters of who I was out in the field with last week, and I should say that two of these people are really the ones that are doing much more work within the area, and I was kind of tagging along for the field work and will kind of assist with some of the analyses. But one of the main people is Andrew Zuza, that's shown here in the blue shirt, who's about to take, it looks like, a foliation measurement. Andrew is a faculty member at UNR and in the Nevada Bureau of Mines and Geology. He's doing a lot of mapping within the core complex as part of USGS state map funding. In the background here is Lizzie Langdon-Lassane, who's a UNR PhD student who was there as a field assistant and just to get exposure to these really cool rocks. And then on the right here, holding his iPad and doing lots of StraboSpot work, is Drew Levy, who is another UNR PhD student. And we were really out there as part of his PhD work, where he is collecting samples in particular samples of cross-cutting leucocratic material, and using the geochronology or the results from that to hopefully kind of better estimate how the deformation changed through time. And then in addition, we were focusing on collecting samples for new thermobarometry from regions of the core complex that really lacked this pressure temperature data. And so what I'll show tomorrow is how we use StraboSpot in the field and kind of tips for before going in the field to what we did in the field, and then a suggestion of what I realized I would have liked to have done after we were out of the field. And so in the field, really Strabo is used for describing the outcrops in terms of the petrology, the mineralogy, potentially reaction textures. We also used it for measuring foliation and lineation orientation data. In addition, we took photos within the app so that those photos are always directly tagged to a specific location in that outcrop, and then also use StraboSpot for documenting samples. So tomorrow will be all entirely focused on the StraboSpot. So hopefully this gave you a little bit of context for where the samples are from that I'll be describing tomorrow. Thank you. See you in 24 hours or so.